After the mathematical treatment of the concept of entropy, it would be useful to actually understand what is entropy. So the aim is to actually try to figure out what entropy means, what it tries to tell us about the processes in real life. Entropy expression which we had derived, the expression for entropy change during an irreversible process was S2 minus S1, which is nothing but the change in entropy during the process 1 to 2, is greater than equal to integral of del Q by T. So you see over here that there is an importance given to the heat transfer for the change in entropy. So entropy change has to do with the heat transfer. So we would be understanding as to how the entropy change has to do with the heat transfer. The second important aspect is we see here an inequality sign. Means we say that it is greater than integral of del Q by T if the process is irreversible. It means we are talking about something called as entropy generation, which has to do with the irreversibilities during the process. So in a way, entropy, the concept of entropy is related to two aspects at least. One is the aspect of heat transfer and second is the aspect of irreversibility. We also said that the entropy change expression can be written as integral of del Q by T plus entropy generation, wherein we attribute the entropy generation purely to irreversibility and the expression of entropy change because of heat transfer, we called it as entropy transfer. Now let us discuss this concept of entropy in a bit more nuanced manner. If you look at the isolated system, which is the universe, we would find that the heat transfer of the system at the system boundary is zero because it is an isolated system. And then our expression becomes delta S is equal to 0 if the process is reversible, and if it is irreversible, it becomes delta S greater than 0. What it means is that for an isolated system, this property of entropy whose change will always increase if the process is irreversible, and it would be constant, the entropy would be constant if the processes in the isolated system are reversible. In order to understand this, that how this entropy has to do with the heat transfer, how it has to do with the irreversibility, we need to take a different approach. One is the approach, macroscopic approach, and other is the microscopic approach. For understanding the concept of entropy better, if you look at the Carnot engine and if you look at the temperature entropy diagram, we can figure out that there are 4 processes in the Carnot engine, the Carnot cycle, of which 2 are the isothermal reversible heat transfer phenomena. So for example, the diagram which is seen in front of you, it is a temperature entropy diagram, and that diagram shows us that there is an increase in entropy from S1 to S2 during the isothermal process of heat transfer. Now, from this one can gather that whenever there is a heat transfer, you find that there is an increase in entropy. So the heat transfer phenomena has to do with entropy change. This is one finding which we can understand. This can also be understood from the basic expression of entropy change, which is ds is equal to dq by t, where if the dq is more, if the dq happens, then the ds would change. Okay, so either way, either by referring to the Carnot cycle or by looking at the very basic expression of entropy change, we can figure out that entropy change has to do with the heat transfer. We need to keep in mind that in this diagram, you'd find that the entropy is increasing from S1 to S2 during one process, and it is decreasing from S3 to S4. Now, how come is the entropy decreasing? So you look at it, and you find that when there is a Q in, when there is heat being supplied to the working fluid, there is an increase in entropy from S1 to S2, and when there is a heat rejection from S3 to during the process S3-4, during the process 3 to 4, then there is a decrease in entropy from S3 to S4. Okay, so if the heat is being transferred to the system, the entropy is increasing. If it is being rejected by the system, the entropy is decreasing. So one thing now is clear to us, that whenever there is a heat transfer to the system, there is an increase in entropy because of entropy transfer. So along with the heat flows the entropy. If the heat flows in, the entropy would flow in. If the heat flows out, the entropy would flow out. So how is that? How does that make any sense? Okay, so for that we need to associate this concept of entropy with something called as molecular disorder. Now one can think of a system wherein there are some molecules, and if you are supplying the heat to these molecules, then the molecules would go into a random motion. That means that the molecular disorder would increase. So if the process 1 to 2, even if it is an isothermal process, but because there is a heat transfer during the process 1 to 2, we can expect that the molecules move far apart, and there is an increase in the molecular disorder. And in a way, we find that this is in a way related to the entropy increase, because we said that during 1 to 2, there is an increase in entropy, and we also find that during 1 to 2, there is an increase in the molecular disorder. Similarly, if you consider the process 3 to 4, what we find is that there is a compression process, and also the heat is being rejected. So when the heat is being rejected, the arrangement of molecules would be more compact, the randomness would decrease, and the entropy would decrease. So now, in a way, we are coming to a conclusion that the entropy change, two things we are coming to conclusion, that the entropy is changing because of heat transfer, and the heat transfer has to do with the orderliness of the molecules in the system. And we also, we are saying that if the molecular disorder is increasing, which happens during the heat transfer, the entropy is increasing. Okay, so now we are getting some significance of the concept of entropy, relating it to the heat transfer phenomenon. We also see that in the Carnot engine, when there is no heat transfer, as in the process 2 to 3, and in the process 4 to 1, the entropy is not changing. You look at the diagram and you find that they are vertical lines of the temperature entropy plot, meaning that the entropy remains constant. And why is that so? Because there is no heat transfer. Also, you will find that the processes are reversible. So now, in a way, we are saying that the entropy is changing either because of heat transfer or because of irreversibility. Okay, so by studying the Carnot cycle, we, in a way, can say that the entropy can increase either by heat transfer, as we see during the processes 1 to 2 and 3 to 4, or it does not change if the heat transfer is absent and if the irreversibilities are not there, as we had seen during the reversible expansion process and reversible compression process, that is process 2 to 3 and 3 to 4 to 1. Okay, so what comes to our mind is why entropy is changing because of heat transfer. Then why is it changing during the irreversibilities, and whether the entropy would change or not if there is simply a work transfer. So these practical kind of questions would pop in our mind as to whether the entropy change has anything to do with the heat transfer. If so, why it has to do with the heat transfer. Mathematically, we had already proved that it is happening, but from a physical understanding, to get a physical insight, what exactly must be happening when there is a heat transfer? What exactly is happening when there is a irreversibility? Why is the entropy changing? So this concept of entropy, heat transfer, okay, and irreversibility can be linked to the concept of disorder. You look at this schematic wherein I have shown the molecules which are arranged in a disorderly manner and the molecules which are arranged in the orderly manner. So concept of entropy is better understood from the statistical viewpoint, and we can in a way say that entropy is a measure of degree of disorderliness or randomness within the system. So now if you define it that way, if you try to understand the entropy concept from this angle, this perspective of statistical thermodynamics, and then we can now start making some sense regarding what we were discussing earlier. So for example, we said that because of heat transfer, there is an increase in entropy. So along with the heat, we said there is an increase in entropy. Now, why should that be happening? That is because if you supply the heat to the system, the internal energy would increase and the molecules would be then arranged in a more disorderly state. Okay, because of the supply of energy, there would be more disorder within the system. The molecules would be in more disorderly state, and as a result of that, we can say that because of the heat transfer, the entropy of the system is increasing. Just the opposite, if there is a heat rejection by the system, the internal energy would decrease, the molecules would then be possessing less energy and they would be then in a more ordered state. Okay, so the change in internal energy because of heat transfer can explain the orderliness and disorderliness of the molecules, and in a way we can relate it to the concept of entropy. So I would say that when the heat is being transferred, the molecules would start dancing, there would be more disorder, and the entropy of the system would increase. If the heat is rejected, the molecules would come to a lower level of randomness, and because of that, the entropy of the system can be said to have decreased. So with the flow of the heat into the system, the entropy increases because of increase in randomness, and because of the flow of the heat away from the system, the entropy of the system decreases because of the decrease in randomness. Okay, so this is how we can physically explain why there is an entropy change because of heat transfer. The other point we said was to do with the irreversibility. Before that, this schematic helps us to understand that when you are heating this, for example, in the gas would result in expansion phenomena. The molecules would spread out, okay, and the molecular disorder would increase and the entropy would decrease. If there is a work transfer and when the heat is being rejected, as happens in the Carnot cycle, then because of the heat rejection and the molecules coming closer together, that would decrease the molecular disorder, that would decrease the randomness, and the entropy would decrease. Okay, so this is what we had already discussed when we discussed the Carnot engine. Okay, so understanding of this relation of heat transfer and entropy transfer has to be clear in our minds. The other important concept, as I said, is the entropy is to change, or there is an entropy generation because of irreversibility. Now, how has it to do with the understanding at the molecular level? So when there is a friction, for example, irreversibility is because of friction, then the internal energy would increase, and that would result in the molecules being arranged in a more disordered state. Because what happens is that because of friction, the work would be dissipated in the form of internal energy. That is, it would be wasted in the form of some internal energy increase, and because of friction, because of irreversibility, and then because of that, the molecules would be arranged in a more disorderly state. So if there is an irreversibility associated, there is more disorder, and when there is more disorder, one is to get less work output because of entropy generation. So we know that when you talk about an expansion phenomena, which is reversible expansion, and compare it with the expansion phenomena, which is an irreversible expansion, then you would find that there will be less work output during the irreversible expansion work. That is because there is an wastage, and that wastage is captured by the term of entropy generation. And this entropy generation would be more if there is more irreversibility, and it would be less if there is less irreversibility. So this concept of entropy and its understanding at the molecular level helps us to appreciate that entropy change and entropy generation because of heat transfer and because of irreversibility respectively can be quantified and can be understood better from the statistical perspective also. Okay, so I hope that we have started understanding what exactly is entropy, the property indicating, and also its usefulness in the real life engineering problems. Thank you very much. Bye for now.